Okay, let's dive into this. Welcome to today's High Yield Explainer. If you're tackling Class 12 chemistry, you already know the solutions chapter is packed with concepts that examiners literally love to test.
Are you ready to master this? Today, we're doing a rapid conceptual breakdown of the absolutely critical MCQs and assertion reasoning points you need for your board exams. These are the golden nuggets pulled straight from the NCERT material, designed to trap you. But hey, not after today.
Section 1. Basics of Solutions.
So, let's kick things off with the solvent. It's simply the component of a solution that's present in the larger amount, meaning it's got a greater number of moles. Naturally, the stuff in the lesser amount, that's your solute. And here is a crucial note for your MCQs. Water is universally known as a universal solvent. Lock that fact in. Now, mole fraction is a strictly unitless quantity. I cannot stress this enough. This is one of the most common traps in exam papers. When you're frantically calculating mole fraction in the heat of a test, it's so easy to accidentally slap a unit onto your final answer. Don't fall for it. It is entirely 100% unitless.
Section 2. The Temperature Factor.
Now, what's really interesting about this slide is how heat changes things. Molality and mole fraction, they are strictly temperature independent. They really don't care about heat at all. Molarity, on the other hand, is strictly temperature dependent. The specific relationship you've got to memorize is that molarity actually decreases as you crank up the temperature. Why? Well, heating a liquid makes its volume expand, which dilutes the overall concentration.
Section 3. Gas laws and solubility.
Okay, there's a really strict step-by-step logic to how this works. Step 1. You increase the temperature of a liquid that has a gas dissolved in it. Step 2. This directly causes Henry's law constant, that's Kh, to increase. And step 3, because Kh goes up, the gas solubility fundamentally goes down. It's a total chain reaction. Basically, heating the liquid expels the dissolved gases. You absolutely must remember this chronological chain of events for those tricky assertion reasoning questions. Let's look at a pretty fascinating real-world application of this exact science, 11.7%. That is the precise amount of helium added to scuba diver air tanks. But why? Well, helium has an extremely low solubility in blood, so by adding exactly 11.7% helium by weight, we completely prevent those dangerous, sometimes deadly bubbles from forming in a diver's bloodstream when they're down under intense pressure underwater. Now, here's a brilliant conceptual crossover that shows up in exams all the time. Both of these laws deal with pressure and mole fractions, right? But if you mathematically align their constants, meaning when Henry's constant Kh perfectly equals the vapor pressure of the pure solvent P0, then Raoult's law literally becomes a special case of Henry's law. They just mathematically overlap perfectly.
Section 4. Azeotropes and deviations.
Azeotropes are so fascinating because they have the exact same composition in both their vapor and liquid phases. Because of that, they boil at a constant temperature. And this brilliantly illustrates why standard fractional distillation completely fails here. You simply cannot separate them using normal boiling methods. These stubbornly inseparable mixtures only pop up because of very large deviations from Raoult's law. Notice the stark inverse contrast here. It's really important. A negative deviation from Raoult's law gives you a maximum boiling azeotrope. Conversely, a positive deviation results in a minimum boiling azeotrope. So negative goes with maximum and positive goes with minimum. It's totally flipped. Make sure you hit your NCERT textbook hard to memorize the specific chemical examples for each of these.
Section 5. Properties and Van 't Hoff.
So, the crucial point is, relative lowering of vapor pressure is a colligative property, but simply the lowering of vapor pressure, that is not. Guys, this is a massive trap in exam papers. The relative part, often abbreviated as RLVP, is the whole reason it's a true colligative property. Regular LVP just doesn't qualify. Please do not get caught out by this wording trick. To calculate these properties accurately, we have to use the Van 't Hoff factor, represented by a lowercase I. It's simply the mathematical ratio of the observed value of a colligative property compared to its theoretically calculated value. Think of it like a bridge. It's the bridge between what we expect to happen on paper and what's actually happening right there inside the chemical solution. Let's see how that I value actually behaves for a non-volatile solute. When a solute undergoes dissociation, meaning it's breaking apart into smaller ions, the Van 't Hoff factor becomes greater than 1. But when the solute undergoes association, meaning those molecules clump together, the factor drops below 1. Breaking apart pushes it up, clumping together pulls it down.
Which brings us to our final thought. How will you use the understanding of these invisible chemical forces to ace your exams and really master the physical world around you? Everything, from scuba diving tanks to boiling liquids, relies on these precise rules. Review these concepts thoroughly. If you found this explainer helpful for your board prep, please make sure to subscribe and like to me so we can keep bringing you these high-yield conceptual breakdowns. Keep studying hard, and I'll see you in the next one.